rational functions and equations look when graphed. We're going to solve for rational equations. And notice here I have in bold, what is the difference for solving rational equations versus solving rational inequalities? So we're going to talk about both situations here. This first one, I have a rational equation since we have an equal sign rather than an inequality sign. And notice how I say that we need to be careful of extraneous solutions. Extraneous solutions meaning that when a solution appears, if we have more than one, that we have to exclude it because we know it's not in the domain. So when I'm looking at my denominators here and I'm wanting to solve, I'm going to use the technique of eliminating the denominators to do so. Taking a look at our denominators though, when I'm looking at the domain, our domain, we notice with x minus 1 that x cannot be positive 1, because if I were to take 1 minus 1, we would have 0. So we want to make sure that all of the solutions we obtain are certainly in our domain from negative infinity to 1, and then from 1 to positive infinity. I'm also going to want to look at my least common denominator so that we can multiply and eliminate our denominators. I have my denominator of x minus 1 and 2, so the common denominator will be 2 and x minus 1. So to eliminate the denominator, I'm going to multiply every single thing by that common denominator. When I multiply 2 times x minus 1 times our first fraction here, notice that our x minus 1s will eliminate because they are a common factor. So we were only left with is 2 times x cubed minus 2x plus 1 equals. Now when I take our least common denominator and multiply it by half x, this time our 2 and our 1/2 will eliminate because 2 times half is 1. And we are left with the lonely x times x minus 1. Finally, when I multiply by the last term, I have negative 1 times 2 times x minus 1. Notice nothing will be eliminated, so negative 2 times x minus 1. By multiplying everything by the least common denominator, notice we were easily able to eliminate all of our denominators in order to move forward. Let's go ahead and simplify here by distribution. So we will have 2x cubed minus 4x plus 2 equal to x squared minus x minus 2x plus 2. We can go ahead and combine like terms on the right-hand side. 2x cubed minus 4x plus 2 is x squared minus 3x plus 2. Well, I know that if I'm going to solve this, I will in fact need to get all of my terms to one side. I'm going to leave my 2x cubed positive, so I'll subtract x squared, add 3x, and subtract 2, bringing that to the left-hand side, so that we have 2x cubed minus x squared minus x, and then my 2's will end up canceling since it'll create a pair of zeros equal to 0. I do have a common factor of x. We will factor out x, leaving us with 2x squared minus x minus 1. Perhaps I could factor the inside quadratic, so two numbers. Since we have a number in front of x squared, we need to use the AC split method. So two numbers that multiply to negative 2 and add to negative 1, or negative 2 times 1. I'll split my middle term into those magic numbers of negative 2x plus 1x minus 1. We now have 4 terms, which we can factor by grouping. My first two terms are divisible by 2x. So when we divide by 2x, we are left with x minus 1. I'm going to divide my second set by positive 1 so that it remains the same. Ultimately, our goal is to make sure that we have a common binomial that we can factor out. When I factor out my common binomial of x minus 1, we will have 2x plus 1. Don't forget we originally took out the greatest common factor of x and set it equal to 0. We know that once it's factored, we can set each factored piece equal to 0 and then solve each one individually. So I have x is equal to 0, x will be equal to positive 1, and then x will be equal to negative 1/2. We had to be careful. We set up here that x could not be 1 because when we substitute 1 back into the original equation, it's not part of the domain. So we are not going to include 1 because it is not part of our domain. So our two solutions are 0 and negative 1/2. Moving on to slide number 2, I have two different ways we could solve this utilizing graphing. The first method is the 0 method, where I would subtract the 1/2 x and then add 1 so that our equation is set equal to 0. The 0 method then, find the x-intercepts. Where does our graph cross the x-axis? We found 0 and negative 1/2 were solutions. Notice that there is a hole in our graph where it is undefined. The second method, so I'm going to put the word or here, or we could graph the left-hand side, which was the x cubed minus 2x plus 1 over x minus 1. And on the second line, I'm going to graph the 1/2 x minus 1 and determine where they intersect. So the intercept method is to graph the left of the graph and graph the right of the graph and identify where they intersect each other. Notice they're intersecting each other again at 0 and at negative 1/2. 1 is also still undefined because it is undefined with our red graph. So the quadratic is where it is undefined, so that is why it is undefined on the red line and not undefined on the blue line. Let's look at another example, example number 3. This time I have the exact same thing, exact same solutions that I had before, except this time I have the greater than or equal to sign. It's asking us to be careful of extraneous solutions. Further, to find the critical values where x is undefined and where the function as a whole is equal to 0. We already know where x is undefined, so x is undefined at x is equal to 1. We know where the whole is equal to 0. If I were to have subtracted x cubed minus 2x squared plus 1 over x minus 1, and we subtracted 1/2 x and then added 1. When we solved this earlier on our first example, we saw that x was equal to 0. And x was also equal to negative 1/2. So we found all of our critical values, where it was undefined, and where the graph as a whole was equal to 0. So we're utilizing the solving piece with the equal sign to help us identify where all of our critical values are. Once I have my critical values, I'm going to create a table or a line, if you will. I'm going to create an x-axis to help us identify where our graph is positive or negative. Notice here when I started to solve that I'm looking for values that are greater than or equal to 0. So we're only interested in when our graph is positive. I'm going to utilize my critical values to place them on the graph. So -0.5, 0, and 1. I'm then going to choose values in between those two pieces because we actually have 4 intervals. 4 intervals. What happens between -infinity to -0.5, between -0.5 and 0, between 0 and 1, and between 1 and infinity? Where are they positive and negative in these locations? So my test values I'm going to use are -1, -1/4, half, and then let's say 2. So I'm choosing values that are in between the two areas there. I also know that at -0.5, I'm going to have, because we can have a solution at -0.5, so it's going to be a closed circle. At 0, we also know it's a closed circle because it is included as it is a solution. However, 1 is where our graph is undefined, so we're going to use a hole. So what happens in between? What happens in between is the following. I am going to substitute into my function -1. So when I substitute, let's say this is g of x, I'm going to substitute g of -1 into my my graph here, and I'm going to use this value here since all of the pieces are on one side already for me. I don't need to do any extra steps. When I substitute g of -1, I know you can utilize the order of operations to do this, as well as utilizing a calculator to do this. When I do this, then my graph ends up being a positive value. It doesn't matter what number that is, we just know that it is positive. When I substitute g of -1/4 in, I end up with a negative result. Again, it doesn't matter what the value is, I end up with a negative result. So I'm negative under here. Now when I substitute half into my function, half provides me with a positive solution. So between 0 and 1, we are positive. And then what happens when we are going from 1 excluded to infinity? I'm going to use my test value as g of 2. When I substitute g of 2 in, I end up with a positive value. Doesn't matter what that number is. We're just looking for positive and negativity. So my solution set goes from, again, we're looking for only positives. So these are the ones that we are only interested in when I'm looking at my endpoints here. So my solution set goes from -infinity to -0.5. Notice I'm going to use a bracket because we have a closed circle. I'm going to skip over between -0.5 and 0, and I'm going to start back up again at 0. And I do have to go to +1 because 1 is excluded. And then I'll pick back up at 1 and go to positive infinity. So all of these solutions would work with our graph. Let's take a look at what the graph would look like. Again, here we are looking at the 0 method. So I'm looking for where I set it equal to greater than or equal to 0. I can see that my graph is greater than or equal to. I can kind of look at this as almost not an asymptote, but a cutoff part, because in here, my graph is positive. And then notice that it dips down negative between here, just as we indicated. It becomes positive again. But then notice that we have to skip that undefined part and then continue going positive. Or we could utilize the intersect method. We're going to graph the left and the right hand side. And we're looking for where is the left-hand side greater than or equal to the blue line. So where is the red line greater than the blue line? Again, -1/2 is that cutoff part. So notice the red line is above the blue line from -infinity to -1/2. Then my red line goes below the blue line. But then it becomes positive again, where we skip the undefined portion and then we continue positive again. So 2 different methods for what we're looking at. Let's try another example. Here I have x minus 3 over x plus 4 is equal to x plus 2 over x minus 5. We have some extraneous solutions we have to be careful for. We have to be careful when x cannot be -4 and it cannot be 5 because of our denominators. So our domain is from -infinity to -4, from -4 to 5, and then from 5 to positive infinity. So as long as our solutions are in our domain, life is great. I also am looking at my denominators to identify what is my common denominator. Well, my common denominator would have to be x plus 4 and x minus 5. Looking at all of the different factor combinations. I'm going to multiply everything by that least common denominator of x plus 4, x minus 5. When I multiply my first term by x plus 4, x minus 5, I know that my x plus 4s will eliminate because they are a common factor and everything is being multiplied together. All we are left with is x minus 5 times x minus 3. When I multiply by the right-hand side, this time my x minus 5s disappear, and I'm left with x plus 4 times x plus 2. You could also cross-multiply and equal them to one another. So you could also cross-multiply and set them equal to each other, and notice you would end up with the same result. So there's a couple ways you could have tackled this piece together. Let's go ahead and distribute. On the left, we will have x squared minus 3x minus 5x plus 15. And on the right, we'll have x squared plus 4x plus 2x plus 8. Simplifying, I have x squared minus 8x plus 15 and x squared plus 6x plus 8. We know that if we're going to solve, it has to be set equal to 0. I'm going to take my right-hand side and subtract it to the left. You certainly could go from left to right. It doesn't matter. When I do that, though, I'm left with no x squareds minus 14x's plus 7 equal to 0. Solving then by subtracting 7 and dividing by -14, x is equal to half. Half is in our domain, so so our solution, if this was equals, is simply going to be half. Utilizing the 0 method I have on the right, I subtracted the right-hand fraction or rational expression and moved it to the left, and identified where does my graph equal 0. Or I graphed the left-hand side and the right-hand side and identified where the red and the blue lines intersected each other, which is also at half. So either way works. By doing it this way, the red line would have at x is -4. We can't see it. It would be up here. There would be a hole in our graph. But it also, not a hole, excuse me. When I'm looking at the left-hand side, we do have an asymptote at -4 with my red graph. And we also have an asymptote with the blue graph at x is 5. So that's where those pieces are coming from. And you'll also see, if we were to use the zero method, that we do have a asymptote at -4 and at +5 as well on that graph. Let's move to slide 6, where we can talk about solving utilizing inequalities. It's asking us to find the critical values where x is undefined and where the function as a whole is equal to 0. Well, we've done all of those pieces. We know x is not defined, so x cannot be -4 or 5 since it's not in the domain. And when we solved for 0, we had x is equal to half. So here are all of our critical values. Let's create our x-axis here, where I'll use my critical values and create a number line of sorts. I know that x cannot be -4 and it cannot be 5, so we'll use open circles in these instances. And at half, it certainly can be, so I'm going to use a solid circle. I need some test values in my intervals. Let's use -5, 0, some nice easy values to help us out. When I evaluate, we are looking for values that are less than or equal to. So I'm going to say that our function, let's call it f of x, is x minus 3 over x plus 4, subtracting the right-hand side. And I'm looking for, where is this less than or equal to 0? So we're looking for negative values that will make our equation true. When I substitute, and I know you can do this, so I'm going to let you do this part on your own. When I substitute, let's say -5 into our function here, we end up with a positive value. When I evaluate at 0, I end up with a negative value. When I evaluate at 1, I have a positive value. And when I evaluate at 6, we have a negative value. Not -1, just a negative value, excuse me, a negative value. Doesn't matter what the value is, it's just positive or negative. We're looking for where our value is negative in our solution set. So when I'm looking at my chart here, I see that there are 2 locations with which our graph is negative. So the solution set as a whole is from not included -4 to +0.5, which is included. Skip over a bunch, 5, which is not included, to +infinity. So as I'm looking at the zero method when I'm graphing, and the intersect method when I solve, we want to again look for where is our graph less than or equal to 0. We have our asymptotes here that we talked about on the last page, and the asymptote at 5 from the last page. So where is our graph as a whole less than or equal to 0? So our graph as a whole is less than or equal to 0 between, again, -4 not included to half, which is included. We skip over, and then our graph becomes negative when we're from 5 to infinity. Or I can ask myself, where is my graph, my red graph, less than or equal to my blue graph when we do the intersect method by setting them each equal to 0. So I can see that my red graph is smaller than my blue graph, going from, again, here's our asymptotes. My red graph, the left-hand side, is less than the right-hand side from here to here. And then again, my red graph is less than my blue graph in this area. So another way in which we can utilize the graphing to help us. Let's move on to slide 7. Let's solve 1 over x squared plus 1 is equal to 0. Be careful for extraneous solutions. We do not have any extraneous solutions because our domain is from negative infinity to positive infinity. There's nothing that I could substitute in for x squared, which would make, and then adding 1, which would make our graph 0 in the denominator. So we don't have any extraneous solutions. Let's go ahead and start solving. To solve, I would want to multiply the left and the right hand side by x squared plus 1, providing me with 1 is equal to 0. Well, 1 is equal to 0 is false. So there are no solutions. Similarly, when I want to solve 1 over x squared plus 1 is less than 0, when is my graph less than 0? No solution here as well. And look at the picture on the right-hand side. Notice that we have y is equal to 0 is in fact a asymptote. So our graph is never going to get below the x-axis. So our graph is never below 0. So there's no solution here. And since our graph is never below 0, it's always above 0, we're not going to have any x-intercepts to solve for this. However, if I had 1 over x squared plus 1 is greater than 0, I could say that our graph is greater than 0 would be our entire solution set, since I can visually see that our graph is above the x-axis for its entirety. Let's look at one more example. Here I have negative x cubed plus 4x over x squared minus 9 is greater than or equal to 4x. So this time I don't have the equal sign. However, we are also solving at the same time as we are utilizing the inequality piece. So regardless, we want to be careful of extraneous solutions. I know that x squared minus 9 is the same as x plus 3, x minus 3. So I know that x's cannot be 3 or negative 3, the only place in our graph that is true. So our solution for our domain has to be between negative infinity to negative 3, from negative 3 to 3, and then from 3 to infinity. So whatever our solutions are that we obtain have to be within our domain. I'm then also going to take negative x cubed plus 4x over x squared minus 9, subtract the 4x because I'm interested when our graph is greater than or equal to 0. So we already found where our graph cannot be 0. But we also need to find the other critical values. So we also already found where it's not defined. So we just need to identify where our entire graph is equal to 0. So to do that, I'm going to multiply by our least common denominator. And our least common denominator I do see is the x squared minus 9. So we're going to multiply everything by x squared minus 9. When I multiply my first set by x squared minus 9, our x squareds minus 9 disappear. And all that is left is negative x cubed plus 4x. When I multiply x squared minus 9 by negative 4x, nothing simplifies. So I'll have negative 4x times x squared minus 9 is greater than or equal to 0, since anything times 0 is 0. We now are able to distribute negative x cubed plus 4x minus 4x cubed plus 36x. Combine like terms, I have negative 5x cubed plus 40x. I do see at this point that we have a greatest common factor of negative 5x. So I have x squared minus 8. It's in factored form, so I can set each piece equal to 0. So far x is equal to 0. 0 is in our domain, so that is a good sign. I also will have x squared minus 8 is 0. So x squared is positive 8, and x is plus or minus the square root of 8. I know I can simplify the square root of 8 into 4 times 2. And the square root of 4 is 2 with square root 2 left over. We have a few places then when we are creating our x-axis here. We have the solutions, putting them in order, things that we need to be aware of. We'll start with negative 3 from where our graph was undefined. The next largest value is negative 2 square root 2 from our solution set. We then will have 0, which we found over here. We then have positive 2 square root 2 from our positive solutions, and then we'll end with 3. Negative 3 and positive 3 will be excluded because they cannot be in our domain, whereas the rest are good solutions and are in our domain. So when I'm looking for test values, I need 6 of them. I need at negative 4, so what happens below negative 3? Negative 2 square root 2 is approximately negative 2.28, so in between we have a very small window of negative 2.9 in between. I can use a test value of, let's say, negative 1 here, positive 1 then, and then 2.9 here, as well as 4. So my test values. Let's again call this f of x, and f of x could also be the same as down here. We're looking for values that are greater than or equal to 0, so we're looking for only positive solutions. When I substitute negative 4 in, we end up with a positive value, so that's good. When I substitute in negative 2.9, we end up with a negative solution. When I substitute negative 1 as my test value in, we have a positive solution. When I substitute 1 in, we end up with a negative solution. And just because, I want to warn you that just because we are alternating here is not always going to happen. So do not assume it's going to be alternating like we are now. You have to check. When you substitute and use the order of operations for positive 2.9, we have a positive solution. And then finally, when I substitute positive 4, we have a negative solution. So we have 3 areas where our graph is positive. Our final solution set then is from negative infinity to negative 3 excluded. skip over. We are included at 2 square root 2 to 0, and 0 is also included. We skip over a bunch to, this was negative, excuse me, negative 2 square root 2. Start again at positive 2 square root 2 to positive 3. My graph here, I subtracted, so I'm utilizing the portion with which our graph is greater than or equal to 0. So our graph is greater than. I had to zoom out a bit to understand and see this, that I have my graph is greater than or equal to 0 between negative infinity and negative 3. And negative 3 is where an asymptote would be, even though it's pretty difficult to see. We would skip over that portion and we would have another little bit here from negative square root 2 to 2, square root 2 and 2 to 0. We then go negative, but then again we go positive one more time from square root 2 to 3, even though we can't see that 3 is over here. We are positive in this area, and then we dump down into the negatives down below. So I had to kind of move out my graph a little bit so that we could see all the moving pieces, the little juts at the top and at the bottom to verify the positive and negativity. But that concludes our lesson on 4.3, and this is the last piece of your lesson for graphing rational functions.